All right. Right here at the bottom of the page is where we're starting, and we'll get through all of them. So the two blanks right there are exactly what I asked on the journal today. Mixtures and pure substances, that's right. Pure substances. Those are kind of the first way that we divide matter. Matter which order they are. Alrighty. So then we have our little flow chart next. And this just asks some questions and you answer them and it tells you which way to go on your flow chart. So first one, can it be physically separated? Physically separated is like just maybe being able to pick it apart. Maybe you could evaporate off the liquid and have the solid at the bottom. Filtering, those are physical means. If it cannot, then we move to the pure substance side. And that's actually where we'll spend most of our time in the year. Then our next question, can it be chemically decomposed? Can it be broken down chemically? If the answer is no, then we have our element. Anything on the periodic table. It would all have symbols. Now we know that elements of atoms are made up of protons, neutrons, and electrons. But this says, can it chemically be decomposed? To get to protons, neutrons, and electrons, it have to be some kind of nuclear process. If it can be chemically decomposed or broken down, then we go to a compound. So a compound is two or more elements. So these are going to have a formula. So if I give you something and it has just a symbol, that's a hint for you that it's going to be an element. And then if it's a formula, then I'm going to give you the formula. Things like sodium chloride, glucose, those water, obviously, those would be things that you should know. So if we look at that, H2O, that is a formula. I break that down. I would have just hydrogen and oxygen. Those are elements. Now, if we go to the other side of the flow chart, it says, can it physically be separated? We say yes. Then it is called a mixture. After we decide it's a mixture, is the composition uniform? So that means, is the composition the same throughout? If it is, then it's going to be a homogeneous mixture, also called a solution. Those two are interchangeable. Solution is equal to a homogeneous mixture. Remember, whenever we talk about a solution, there's two parts to it. The solute, and that's what is dissolved. And then the solvent, one does the dissolving. Think of salt water. Salt's going to be the solute. The water is going to be the solvent. All right, now on the other side of the mixtures, that's where we have most of our things. If the composition is not uniform, then we say it is a heterogeneous mixture. Hetero means difference, that prefix. So just a real typical one would be trail mix. With a heterogeneous mixture, if I had some and I gave everybody a sample, it's going to be a little bit different. And then under heterogeneous mixture, you're either going to have a suspension or you're going to have a colloid. And those differ in the size of their particles. And we'll talk about that more, of the solid particles. We'll talk about that more as we move on through the notes. All right, let's do pure substances first. So a pure substance can either be a compound or elements. They cannot, pure substances cannot be separated by physical means. And they are uniform in composition, and that is called homogeneous. It doesn't say that elements or compounds are homogeneous mixture. They're homogeneous in appearance. So that first blank is where you're going to put elements. Elements. So these are composed of identical atoms. They cannot be decomposed by just a chemical change. So an example of that would be iron or its symbol Fe, carbon, anything off the periodic table. These are homogeneous in appearance. Appearance. So a homogeneous mixture is a mixture of things that are put together, not chemically bound together, and they look the same throughout. But other things can have a homogeneous mixture. So like water, that's a compound, but we know it has a homogeneous appearance. If I had a gallon of water and I gave some to everybody, it's going to look the same. So homogeneous by itself just means it's going to be the same throughout. Compounds, going to be our other one. They're composed of two or more elements in a fixed ratio, like a recipe. They can be decomposed by chemical changes. That's what we do our chemical reactions with. And their properties differ from the individual elements. And like I said, it's going to have a chemical formula. So whenever you get to some of your practice, you'll see some of them have chemical formulas. And also on the quiz or the test, then I try to give you the chemical formula if it's something that you may not be aware of. So salt, which is sodium chloride. Water, which is H2O. Those are all compounds. Good old glucose, H12O6. That's a compound. And they are also I know that's right. That's why you'll see I bring it up some. They are homogeneous in appearance. But they're going to be the same throughout if I have a sample. We can have a couple of laws that kind of guide compounds, and we'll talk about these laws, and we'll probably come across some later on again. Everybody got this? I'm going to move it up a little bit. Yeah. All right. So the law of definite composition, it says a given compound always contains the same fixed ratio of elements. So it's like it's a recipe. If I want to make water, which can't really happen, but if I did, I'm going to have 2 hydrogen and 1 oxygen. That's my fixed ratios. If I tacked on 1 more oxygen, then I would have peroxide. I don't want to drink and cook and everything, wash and peroxide. Yes, I think it was. Last year, hydrogen peroxide, if y'all remember when y'all had a little piece of liver, Miss Gorman, and then we were studying enzymes and put that on there. Yeah, it bubbles, which is also what it does usually if you put it on your little bit open wound. Law of multiple proportions says elements can be combined in different ratios to form different compounds. So if we talk about CO2, that is carbon dioxide. You know, plants need that for photosynthesis, so it's a good thing. But now if I change that up, just the same two elements, but in a little bit different ratio, now I have carbon monoxide, yeah, which isn't so good, which is poisonous. So it's very important how you put the elements together. Like I said, throughout the year, we really spend more time on that. So we're going to talk about mixtures. Mixture is matter that can be physically separated into its component parts. So if I had a bag of M&Ms, that would be a heterogeneous mixture, and I could divide them into all their colors. There are two types. The first one is homogeneous. A homogeneous mixture, not just homogeneous appearance like we talked about before, but an actual mixture. It has uniform composition, and it's also called a solution. Homogeneous and mixture and solution mean the same thing. We'll do a unit just on solutions. All righty. All righty. Here. Here. See if I can make it a little bigger. All right. Although individual, was it homogeneous or heterogeneous? Although individual samples are uniform in composition, it can and does vary from sample to sample. So that's like if you got by Gatorade, it's going to have a lot number on it. Everything in the lot number is going to be the same, but sometimes there's a little difference between lot numbers. That's what we're talking about there. Any substance, whether it's a solid or liquid or gas, that is evenly dispersed throughout another substance is going to be considered to be homogeneous. Particles are very small and they do not settle out and they have no Tyndall effect. That all of this has to do with solutions. Remember, we're continuing on with solutions. So solutions, the solute, the particles are very small. They won't settle out. They won't gather at the bottom and they do not have the Tyndall effect. And the Tyndall effect, because we'll mention it a couple of times, is what happens when light is scattered. So scattered light of a beam of light is passed So in other words, if I have some mixture and I shine a flashlight through it, if it goes all the way through, then it has no Tyndall effect. But if it has some big particles that are kind of floating around in the solution, solid particles floating around in the solution, then those particles, when I put light through it, those particles, the light will get in the way and the light will bounce back and be scattered. So it's like fog. Fog would be an example of that. What do you do when you get in fog with your lights? Yeah. Either turn your brights off, or if you have fog lamps. And the reason that is, if you have your brights on and it is a colloid, yeah, and it's going to hit those particles that are in there, and then it's going to reflect back to you, which sometimes can be blinding. So that's what we're talking about here. That would be the Tyndall effect. And we do not see that with solutions. because everything's going to go into solution. There's not going to be anything floating in the solution. So examples of this would be Gatorade, brass. You may know what brass is made up of. It's a metal alloy, which just means a metal mixture, and it's made up of copper and zinc. Why alloys are made? Does anybody remember what color brass is? I'm sorry? Yeah, it's kind of a gold color. It kind of mimics gold a little bit. Do you think it's as expensive as gold? No, because it's made of copper zinc. So that could be one reason. Also, gold is very soft. If you've ever had the higher, like if you have 10 carat, if you go up to like 24 carat, that means it's going to be more pure as far as a gold. And sometimes if you do that with your ring, you'll take it off and it's bent a lot because it's a very weak metal. So that also is a way to kind of make a stronger metal. Another example, contact, solution, tea, coffee, any of those things. We have particles in there. They're not bound to each other. They're just mixed up. All right. Then we have colloids. Oh, no, before I jump my gun. Heterogeneous. So a heterogeneous mixture. The particles, oh, no. The mixture does not have a uniform composition. There are two types, colloids, suspensions. So colloids, that's spelled Colloids. If you're having trouble reading my writing, let me know, please. All right, so we'll start with colloids. Those are a little harder to describe, a little harder to find. The particles are intermediate in size between the solution, which are very small, and then we'll talk about a suspension, and theirs are large. The particles do not settle out, but they do have the Tyndall effect. So those particles are kind of floating in the solvent instead of settling out. So once again, it's like fog, because fog is an example of one of those. If light is shown through that, then they're going to hit some of those particles and be deflected or bounce back. So fog is an example of it. Shaving cream. Delsum cough medicine. Has anybody ever taken the Delsum cough medicine? It's like, I think it comes in orange and grape. It's over the counter, but it's real thick. It's very sugary, but it has a very thick texture, and that's because it's a colloid. The particles are floating around in it instead of going into solution. The other one are suspensions. So this is probably what you're more familiar with. Particles in the solvent are so large that they settle out unless the mixture is constantly stirred. So the components are visibly distinguishable. So that means if you give it a chance to settle out, you're going to have all the solid on the bottom, and then you'll have the liquid on the top. So example of this would be paint. Let's see, Italian salad dressing. Gentlemen, what's going on back there? Because I don't feel like it's chemistry. I don't feel like it is. Yeah, exactly. For that also, yeah. What about, I feel like everybody always knows this, your pink medicine, you took it when you were a kid?
Pepto-Bismol?
Not Pepto-Bismol, the one that was kept in the refrigerator that you would have had to get a prescription for. So what did you do? What did your parents do just as soon as you got it out? Tastes like bubble gum. They shook it up, right? If you didn't shake it up when it was sitting in the refrigerator, all the medicine would go to the bottom and you really wouldn't get any medicine. So that would be an example of a suspension. All righty, let's draw some pictures. I'm not real good at drawing pictures, so we're going to do the best we can. This is element. So let's just say those are all hydrogen atoms. In a compound, I'm going to try to make something that looks like make something like water. So that would be two little hydrogens, right? And then a bigger water. Not very good. So that's supposed to be a water molecule. Then a homogeneous mixture. So we got to have a couple of things. So let's say that we have something big and a square. And because it's homogeneous, it's very uniform throughout. And then heterogeneous, we can have the same particles, but now they're going to be much more random. Like in your practice, there may be a better picture. If you look at your practice number 8, you'll come across a lot better pictures. All righty. So let's look at these and let's say what they are, these examples. Let's classify them either as a pure substance, or we'll say they're heterogeneous, or we'll say it is a homogeneous, which is the same thing as a solution. So you can put S if you want to. And B, think of the yucky sand that you get at the beach. You think that would be a pure substance, heterogeneous, or homogeneous? Oh, yeah. I think you can buy some sand for like kids' sandboxes. It might be all perfect. Antimony, SB, that's its symbol. So that makes it what? Pure substance. And within a pure substance, element or compound? Element. All right, y'all give those other ones a try. All right, table salt, sodium chloride, what would that be? Pure substance, and within pure substance, it would be a what? Compound. And just to kind of talk about how different the elements are from the compound, sodium, we know that's a group 1 metal. It's very, very reactive. So reactive, it can't even exist all by itself. Chlorine, if you look over there, halogen, very reactive. And it's a gas at room temperature, but if you put them together, you get table salt, which obviously is not reactive at all, something we could eat. So by forming the compound, it really changes the properties. Salt water, homogeneous. Now, I mean, I can see you can argue this a different way, like if you put too much salt in it and there was a bunch at the bottom, but let's just say it was perfect salt water. Brass, what did we say brass was? Homogeneous. Aluminum, pure substance. Burrito, genius. Glucose, pure substance, a good old compound. All right, This that you picked up today, we'll have a quiz over that on Thursday, or if you were having trouble with any of your chemical or physical practice and you have questions, because that's our quiz tomorrow, you can also do that. But these are just a lot of different ways. There's a lot of different samples with different things that you're going to do. But basically, one way or another, you're going to be classifying it as the things that we talked about today. And like I've said before, if you have a question, please ask it, because probably somebody else has that same question.